So what I want to do now is we've got letting A equal this matrix, 9, 5, negative 5, 0, negative 1, 0, 10, 5, negative 6. And so we're going to use technology to find the eigenvalues and eigenvectors for A and determine if A is diagonalizable, and then find S and D such that A equals SDS inverse, and then confirm that A equals SDS inverse. Okay? So a couple things. Let's first find, somebody give me the eigenvalues for A. What are the eigenvalues for A? So we have lambda equals negative 1, and I'm going to actually separate them out. I'm going to write this as lambda equals 4 as the other one, all right? The reason why I want to do this, and this was something I was talking with Natalie about, you switch places, Natalie. That's just not fair. So that I was talking to Natalie about, we need to make sure that we associate our lambdas with our eigenvectors. Why is that important? Louder, please. Jesse can't hear you. Yeah. Distinct eigenvalues have distinct eigenvectors, but it's even more important from a different perspective, right? From a diagonalization perspective. Why does it matter from a diagonalization perspective? Possibly. I mean, if that's the case, why does it matter if we know where the eigenvalues are? It doesn't matter at all. Like if you're writing out S and D, like that the eigenvalues, that we don't know what eigenvalues go along with which eigenvectors? Huh, interesting. All right, so if lambda equals 1, right, what are the eigenvectors that go along with lambda equals 1? Daniel, what are the eigenvectors that go with lambda equals 1? Same deal, like you can't actually access it on symbol. You don't know which one it is? Okay, so it's really important that we know which one it is. All right? So who does? Ruchi, do you know which ones correspond to which? Negative 1/2. 1, 0, and? Okay, yep, I'll agree with that. And then when lambda equals 4? 1, 0, 1, okay? And what I'm going to write here, what's the, so M is the algebraic multiplicity of negative 1. What's the algebraic multiplicity of negative 1? 2, good. And what is its geometric multiplicity? Angel, what's its geometric multiplicity for lambda equals negative 1? All right. You want to help him out, Jerry? 2, how do you know? Yeah, there's 2 vectors, right? There's 2 vectors in this eigenspace. So the eigenspace here, which is made up of negative 1/2, 1, 0, and 1/2, 0, 1, is 2-dimensional. So that means that its geometric multiplicity is 2, right? It's the dimension of its eigenspace. Yes, number of vectors, M equals number of vectors. And then what is M, our algebraic multiplicity for 4? What do you think, Richie? It's the number, it's the degree of the factor inside of the characteristic polynomial. So basically, like if your characteristic polynomial, in this case, our characteristic polynomial ended up being like this. It was our characteristic polynomial, here I'll write it out. Okay, ended up being lambda plus 1 squared times lambda minus 4. So the algebraic multiplicity is that 2 right there. You need your characteristic polynomial. Now, in this case, it has to be 2. This one, like for example, here would be 2. It has to be 2 because we have 2 associated eigenvectors, right? Oh, hold on just 1 second. So we have 2 eigenvectors, right? The only way that you can get your algebraic multiplicity can never be bigger than your geometric one, right? Okay. Excuse me, try that. Your geometric multiplicity can never be bigger than your algebraic one, okay? So like basically the maximum number of vectors that we can have associated with an eigenvalue is the power of the characteristic polynomial, okay? right? So in this case, since lambda equals 4 has 1, we got 1 here, okay? And lambda plus 1 squared, right? Okay, then that would actually give me 2, yes, in terms of my n. Now my n is going to be dictated by the number of eigenvectors, like we said, right? And if m equals n for all of them, we end up with a non-defective matrix, right? We have as many eigenvectors as we have dimension inside of A, then we have a non-defective matrix. Guys catch that? Okay. Does that answer your question, Richie? Now, Cynthia, what was your question? The vectors that go along with lambda equals -1 are the ones that you find when you plug in -1 for lambda, right? So when we plug in -1 for lambda, when we're solving our eigenvectors, we end up with solving for eigenvectors, we end up with these eigenvectors, right? So this is the null space of A plus I, right? Okay. So actually, let's put that here. So the null space of A plus or A minus -1i, all right? That's the solution, okay? That's equal to this, -1/2, 1, 0, and 1/2, 0, 1, okay? So those are the associated eigenvectors with the eigenvalue -1. Right? So like if you think about the process that we go through in order to find an eigenvector, right? What we do is we go through and we find the null space of A plus lambda I or A minus lambda I, okay? And then we go find those vectors, right? On the other hand, the null space of A minus 4i, right? That's the lambda equals, so this lambda equals 4, as lambda equals -1, that one is going to equal 1, 0, 1. Okay, that equals 1, 0, 1. So that's how you know that that is the eigenvector associated with lambda equals 4. Can you guys see that? Yeah. Yeah, if you were actually using a laptop, or if you purchased the app, if you paid the 99 cents with the $2 or whatever it is. So let me show you. I'll show you right here. And so yes, absolutely, it totally is. Okay. Okay. So if I go into eigenvectors, somebody please give me the matrix. 9, 0, 5, -6. Okay, so we go in here like this, press go. Okay, and now what I see here, it gives me my eigenvectors, but when I go down right here to the steps involved, what you see is the eigenvalues for this guy right here. Okay, and it says -1, 4. And then if I, it'll say right here, eigenvectors for lambda equals -1, and it gives you the eigenvectors. And then it says eigenvectors for lambda equals 4, and it gives you the eigenvectors, right? In fact, if you go in here and you show the steps, okay, what you get is the characteristic polynomial as well, all right? And so if I look at the characteristic polynomial, it says, here's the characteristic polynomial, and if I click on here, it actually even goes in and it factors. Oh wait, it's in here. If I go in here where they give me the values, it factors it for me to make it negative lambda plus 1 squared times lambda minus 4 equals 0. On the app, right? Inside of the actual website, it's doing it, and I did not realize that the two of them were actually different. Okay, I will put that in as a a cost for future classes. Future classes, it will cost you $6 to take this class. It will cost you $2 a month for the app. There it is. All right. So there that is. So now let's go back. Does that make sense, everyone? You can literally go in. This is actually, it'll pull everything for you. That's kind of nice. All right. So now we have those values and their associated eigenvectors, right? Okay. Does that make sense how we know which vectors go with which values? Okay. It's really important. It's part of the process, right? It's part of the process. And so, like, for example, on your quiz on Tuesday, you may be asked to find the eigenvectors and eigenvalues and maybe even diagonalize. And so you should make sure that you know which ones are the associated eigenvectors with eigenvalues. Yeah? Yeah, Milo.
I just wrote down a conflicting note. I thought you said M, it says M equals number of vectors.
N equals number of vectors. Sorry, my bad. N is the geometric multiplicity. So in this case, M equals 1 and N equals 1. Right? If we look at our characteristic polynomial, this is L minus 4 to the 1th power. Right? And so hence, that's going to correspond with M. And then N is going to be how many eigenvectors we actually have going on with it. Okay? Yeah, Richie. Right. Mm-hmm. Yep. That is the characteristic polynomial. The characteristic equation is the determinant of a minus lambda I equals 0. Right? It's how we end up going to solve for lambda. Okay? Now that we have this, the next question is A diagonalizable? It's another really good question. Is A diagonalizable? Yes, why? Because A is non-defective. What does it mean to be non-defective? What does it mean to be non-defective there, Johan? Do you remember? N equals M for all lambdas, right? Okay. Simpler. Is there a simpler way to think about it? All eigenvalues are always linearly independent. So no, that's not it. Did that come off as sarcastic? Oh, okay, good. I've been, like I was telling somebody, I've been having this thing. Yesterday, it was Tuesday was really bad. Like I felt like I was treating people like they were stupid. I really felt bad. So, because you're not. This is just hard. Like it's math. It's hard. And being sarcastic is kind of a dick move. It sucks. So, how do we know that A is non-defective? N equals M, but we got N equals M for all, right? All of our lambdas, right? But simpler way to think about that, Hunter? Okay. How about, Luis? How would you think about it being non-defective? How do you think about it being non-defective?
That it needs to have as many vectors as N.
It has as many eigenvectors as the dimension of A. Okay? So if A is a 3 by 3, we need 3 eigenvectors, right? Another way to think about that, if A is 4 by 4, it needs 4 eigenvectors, right? Okay? Another way to think about this is we need to be able to form an eigenbasis. So an eigenbasis, right, is a basis for the entire space made up of eigenvectors. So if we have eigenvectors, right, okay, we need an eigenbasis is a basis made up of eigenvectors, okay? That's what we mean by an eigenbasis. Cool? Cool. Right, think basis, n vectors, n linearly independent vectors form an entire space. That's the idea. Right, so it is, yes? C. What's S equal? So what is that, Jamie? You got to give. You write v1, v2, v3. I'm gonna be like no. Yeah. So tell me what'd you put? Okay. 1, 0. Good. 1, 0, 1. Great. Okay. So there we go on that one. Yes. Now, what's D? Yes, Jamie. What's your question? Hold on. Give me a second. Does S have to be in that order is the question. Does S have to be in that order? Hunter says, at first he was no, and then he said maybe. Yeah, why do you say that?
Just has to match up with D. So you flip them in a different direction, and your D should have to be in that.
You mean the values in the diagonal of D would be in different places? Yeah. So what he means by this, and this is why you need to associate your eigenvalues and eigenvectors. Okay? Because -1/2, 1, 0 is associated with which eigenvalue? -1. -1. So that means that has to be right there. Got that? 1/2, 0, 1 is associated with which eigenvector? -1. So it has to be there. And then 1, 0, 1 is associated with which eigenvector value? 4. You see that? All right. Now what you need to do is say to your neighbor, express to your neighbor what exactly happened. You guys got that? It's a check for your knowledge. Right? Like you kind of sit there going, this is why he just did that. Right? Got it? You can't do it. But I do it. Cool. Like, I want you to, like, seriously, this is the kind of thing that you should be able to tell somebody. Why is it that this D has to look like this? And I don't want, like, the big theoretical one. I just want, like, the eigenvalues with eigenvectors. Got it? Oh, did you? Oh, you already did? And it's, you read minds? Amazing. How about express it, Catherine? So why don't you explain it? Explain it. Practice. I don't need a detailed explanation. I need if I were gonna build S and D, what thing would I have to remember? Do you follow me? Right, I'm betting, like, basically, if I wanted to get this question right on the quiz, right, how would I go about doing that? Got it? Okay. Well, let's say that that's right. Let's assume that that's right. Okay. All right. What do we have to do in order to get that? We don't need to do any more multiplication. What do you mean by matchup? Yes. How so in some of these matrices? So you gotta explain it. You gotta explain it, Angel, right? Come in, Angel's sitting there, and he's like, I don't know how to do this. What if I guess? What can I do? You're like, well, one's the eigenvectors, the other one's the eigenvalues, the diagonal. You're like, okay, great. Is that it?
Yes, consists of.
Is that all? Is that anything that's not the only thing you need to remember, right? So explain what you have to remember. Yeah.
So wherever the D1 and D2 are the first and second value.
Yes, it does. It definitely does have to do with that. Right? Okay. Because we're going to end up with S times D, right? Okay. So we're eventually going to do this thing, right, times this thing right here. Okay. Makes sense? That's true. It does. But all I want you to do is just, I got to make D and I got to make S. Right? Okay. How? Hussein, you too. You got to figure out, like, why is it that we end up with -1, -1, 4 here for this one? This one matches this one. If I switch these columns, I don't get the same D necessarily. Question is why? What do I need to have in action? Right? Okay. Huh? With the? Okay. It has to be placed in the vectors. Huh? The diagonal, right? It's a diagonal matrix, so it's coming out of the diagonal. Yes. Why is the -1 in A11?
Because you can't 1, 0, 1 is equal to the S and the negative S, like the inverse of S. That's how we're doing it. Explaining.
Yes.
It's similar to how this was. Yeah.
What she said was this. She said, if you move, I should actually stop this just as it's sitting around while they're mumbling. So the answer to our question is yes, it absolutely, definitely does matter in terms of, the fact is that if this one here is in the first column, then its associated eigenvector has to be in the first column too. If we switch where our eigenvalues are placed, we have to switch where our eigenvectors are. And if we switch where our eigenvectors are placed, we have to switch where our eigenvalues are. They're connected, right? The placement of the eigenvectors and eigenvalues are connected. And it has to do with what Mikhail said, which is that basically AV equals lambda V. And if we put different V's in, we don't necessarily get AV equals lambda V. So that's kind of the idea that goes along there, right? Now A then is just going to equal S D S inverse. I totally did. I don't know why, but like there's a 0 and there's a 4. There it is. Let's talk about a couple cool ideas. What do you think? Cool stuff that happens. All right. Okay. So if you remember from change of basis, when we did change of basis, that this thing here, this is an eigenbasis right here. Let's first start with that's an eigenbasis, right? It's made up of these 3 vectors. Okay. Yes. So that's a change of basis matrix. This one right here changes vectors in the eigenbasis to the standard basis. Just kind of remember that? Recall a little bit? Yes, we had a change of basis matrix made up of basis vectors, and it changes from the basis into the standard basis, right? So that's that one right there. This one here takes elements in the standard basis, and it turns them into the eigenbasis. When you take the inverse of these, the change of basis matrix, it goes from the standard into the eigenbasis, right? Okay. So what we're looking at here is this first matrix right here, the inverse matrix. What it does is it takes elements in the standard basis, right, and it transforms it into the eigenbasis. Okay. Then what we get is we get stretching, right? Stretching and flipping, right? Because these are negatives, negatives, negatives. So these stretch and flip all those basis vectors. That's what that diagonal matrix does, right? It takes everything that was in the, right, that was in this direction, and it makes it, multiplies by -1, so it flips it. And everything that was in this direction, and it flips it. And everything that was in that third 1, 0, 1 direction, and it scales it by 4, multiplies it by 4. So basically, we transform from the standard basis into the eigenbasis. We did a transformation where we just stretch stuff, and then what does this one do? It takes it from the eigenbasis back to the standard basis. So what we did was basically, that's what a transformation is in many ways, especially an invertible transformation. An invertible transformation basically takes stuff in your original standard basis, transforms it into some kind of basis using these eigenvectors, right? Does stuff to it, yes, stretches, shrinks, flips, right? And then transforms it back into the standard basis, okay? Which is kind of neat if you think about it. It just, we'll do stuff over here, then I'm going to flip it, or I'm going to take something in my regular basis, right? Transform it into something easy to work with, namely my eigenbasis, right? Do what I need to do there, and then transform it back. Cool. Yeah. Yeah, Catherine.
If you switch, like, if you look at the D matrix and the S matrix, so if you switch the column order, and you had that for S and D, you still get the same A, original A.
If we flip the what?
Like, for example, if you look at the second column of S, and say you switched it for the third column, so hence you'd have to do the same for D, right? And then would you still, when you...
And you'd have to do the same as obviously inside the inverse matrix.
Right, right.
Yeah.
So would you still get the correct A?
You would.
Same order.
Totally. Same A, same order.
Right.
All good.
In the case where you find, like, let's say when you're solving for lambda, you just wrote the 4 first off as A11. That's okay as long as you do everything.
Totally fine.
Okay.
Yeah, as long as the eigenvalues correspond with the eigenvectors, right? The column of the eigenvalues correspond with the columns of the eigenvectors. Everything's good. All right. Got a question for you. Without calculating, what's the determinant of A? Nu says 4. Why? Angel says 4. Huh?
The other two form the identity, right?
They're determinants for the identity, yeah. Why is that new? It's the product of the diagonal, so that's the determinant of D. So you're saying that the determinant of D is equal to the determinant of A? Huh?
The first matrix and the last matrix, the inverse, they form the identity, and then the determinant is just going to be the diagonal like in the matrix.
Mostly. Yes, that's true. Although there is a matrix in the middle of it, so we do have to kind of account for that, but that's totally fine. You can't, like, remember that matrix multiplication is not commutative, but it's pretty much the idea. That's pretty much the idea. Yeah. Hunter?
Wouldn't it be easier to say that because one's the inverse of the other, it's just the determinant and then one over the determinant?
That's what we're looking at. Same idea, right? Or very similar idea. Okay? The very similar idea. So what we've got here is the determinant of A, right, is going to equal the determinant of S, D, S inverse, okay, which equals, if you remember our rules of determinant of S times the determinant of D times the determinant of S inverse, right? Now these are all just scalars. Those are scalars, they're just numbers, and so hence we can put those in any order that we want. We can't put any matrix in any order we want, but we can put any determinant in any order we want. You guys got that? Different idea. So this is now the determinant of D times the determinant of S, and then if you remember, and then we'll use the determinant of S inverse, and then that's going to equal the determinant of D times the determinant of S times 1 over the determinant of S. And while you can't divide matrices, these aren't matrices. These are scalars, right? So this just simply equals the determinant of D, right? Which equals -1 times -1 times 4. So that's 4. Bonus question, all right? Okay. What does that mean about the relationship between the determinant and the eigenvalues of A? What's the relationship then between the eigenvalues of A and the determinant of A? Just take a look at it. You guys actually did it. Think about what a D is. What is D? D is not a basis. Well, D is a basis, but like... No. Well, yeah, no, it's not the standard basis. Its eigenvalues are the standard basis. What is D? Literally, we just did. What is D? The diagonal of the eigenvalues, right? And how did you find the determinant of A now? We multiplied the eigenvalues together. We multiplied the diagonal. You guys catch that? Like, to find this determinant, the determinant of D, we multiplied the eigenvalues together, right? Accounting for multiplicity, yes? Okay. So basically, right, if we go in, the determinant is just all the eigenvalues multiplied together. Neat, right? That's cool. Come on now. Fine. places we will go. So determinant of A equals the eigenvalues of A multiplied together. And I'm going to say, and when we say accounting for multiplicity, just notice that we multiplied -1 twice. So you have to do that. So if you have an eigenvalue that has a higher algebraic multiplicity, you're going to have to basically raise it to that power, right? So like in this case, it's determinant of A equals -1 squared times 4. Right? This was m equals 2, and this was m equals 4. What do you think? That, by the way, is only for diagonalizable matrices. If A is not diagonalizable, what's its determinant? 0. Yep, it's not invertible. Huh. There you go. Cool, yes? So, did you have a question, Hunter? All right, great. So